The topic today is when our population is going to finally start shrinking, and we'll look at the formal demography of peak population, the peak being the onset of depopulation. Oops. So some quick thanks. These are going to be too quick, but thank you again for the invitation to the organizing committee and the Wittgenstein Center. This work is co-authored with my good colleague Tom Cassidy, who's at the University of Bucknell. And I did a preview of the app I'm going to show, which we may or may not get to, on Twitter. And so thanks to Carl Schmertmann and the rest of Twitter for comments on the app. And you can play with the app afterwards and write me questions, and I would love to interact on it. This is work in progress. Okay, so let's think of the dialogue of somebody from the outside here. We could have a depopulation, or as I put here, depopulation denier. Someone who says this depopulation thing is a myth. There are lots of countries, even those with few immigrants, that have already had below replacement fertility for a long time, but they just keep growing. Well, we as demographers know that populations might continue to grow after they've reached replacement fertility. And so we would say, oh, but there's age structure. We're in an age structured population. There's a lag. Just you wait. And the goal of today's talk is to give you some insight and some sense of how long the wait is likely to be, and what are the factors that determine how long the wait is, and the factors that don't determine it. So what we'll do today is we'll look at an answer almost 50 years ago by Ansley Cole, where he had a scenario of forever declining fertility. Then if we have time, that's what we're going to spend most of our time on. And then we'll spend a little bit of time on some extensions that Tom and I have introduced for introducing changes in mortality, and also the flattening of fertility decline, or the leveling off of fertility decline. We'll definitely get to the slide where I show you how the real world, or at least forecasts of the real world, look, and how that compares to our formal demography. And then we'll look at some open research questions at the end. So I'm going to skip over migration. I may have one slide on it, but I'm happy to discuss. And we're going to have a couple of interactive features to wake us up in the morning and to challenge me as a presenter to see if I can juggle everything at once. Okay, so where do babies come from? Great question. Of course, the real answer is very interesting. The demographer's answer is less interesting. The demographer's answer is today's babies come from past babies. And we write down that the births at time t are a function of births born X years ago, times, those are the mothers that are alive today, times their survival and fertility. This phi function is the net fertility function or net maternity function. And so the babies born today are a function of babies born in the past. And to make our life easier, now notice I have phi changing with time here. To make our life easier, demographers use an approximation, and Ansley Cole definitely used this approximation. And that is, we say that today's babies come from mothers born about a generation ago or 30 years ago. So, we can substitute mu0 for x, and then take this out of the integral, and then sum over phi, and we get the NRR, which is the net reproduction rate. So what we have is the babies born today are about equal to the babies born 30 years ago times the reproduction rate, the net reproduction rate of those babies. Now, this is not exact, because in a real population with changing demographies, this mean term is going to change a little bit with time, but we can set it next to mu0 and do quite well. Okay, so Cole's scenario worked from this kind of premise of the renewal equation we just saw. And he said, what if the fertility is just declining all the time? And it's declining at some exponential rate k. K is negative, so it's a decline. And at time 0, the NRR is 1, just by definition. We call this T0. And before time 0, the fertility is above replacement. And after time 0, fertility is below replacement. Okay, so that's the scenario he was looking at. He was doing this 50 years ago, and his interest was more in what effect this would have on age structure, rather than, remember, the peak of world population growth, and rather than on actual peak population. But he came up with some results that are very useful for us. Okay, so now we'll have our first question. So here's the NRR declining. It becomes 1 at replacement at time 0. And so I want you to think about for a second when there will be the most births. Will it be before time zero? Will it be at time zero, or will it be after time zero? Now, the way to think about this is before time zero, we have a positive net replacement rate, and so the population is increasing. So the number of moms are increasing, but at the same time, the fertility rate of each new mom at time t is going down with t. So there's kind of a battle between the increasing number of moms and the decreasing number of babies per mom. Okay, so we're going to try something interactive. Open your chat box and type in A, B, or C. And Alexia will look at what you write. Okay, what are people writing, Alexia?
At the moment, C is winning.
C,
now,
okay.
Yeah, C is, I think, the most common answer.
Okay, so we have this idea that there's momentum, it should happen afterwards. Okay, the answer, it turns out, is that it happens before. So let's look at an actual simulation of this. Whoops. Okay, so we can see this. So this is a simulation now of the same curve we just saw, and we can project it through time, real population through time with this fertility rate and see what happens. So let's do this. And here we have the births climbing, 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 and leveling off, and then beginning to go down. So where do they level off? They level off at time -15, or before time zero. Okay, so let's look at this. We can stop our simulation. Just a second, I have to move something. There we go. So we see the births peak right here, okay, actually before time zero. Now we can ask, well, does this depend on the rate of decline? So we can change the rate of decline. No, it's still -15. We can make it less steep. Okay, it's -15.1, but it's always basically -15. So what is going on here? What's going on here is that when the NRR is 1, we're here, and the births are peaking beforehand. So if we plot, for example, the NRR here is going to be like the slope of this line. Okay, so here we're at time, I'm not sure what time we're at, -10, and the NRR is positive. Okay, and here we're at time +10, and the slope is now down, so the NRR is negative. Good. And at time t equals 0, oops, there we go. The slope is 0, where the NRR is 1. Okay, so they're the same number of babies as there are mothers born 30 years ago. And we can see from the curve is going down here at time t, and so the peak is beforehand. So the first surprise of age-structured population is that the number of births actually peaks before fertility reaches replacement. The second surprise is that it doesn't matter how fast fertility is falling, it's always going to be about 15 years, -15 years, which is about half a generation. Okay, so that's our little explanation. And now we'll go back to the presentation. And you can play with this later also and see more about it. Okay, so we learned that births peak before T0, and in this Cole scenario, they actually peak exactly half a generation before, and it doesn't matter how fast the NRR is declining. Okay, so the second thing we're going to do is ask, when does population peak? Okay, and we're probably a little bit behind in time, so we'll just consider, we won't do the chat this time, we'll just kind of consider some possibilities. The first one is at the same time as births. The second one is about 40 years later, when the biggest generation reaches the average age of the population. And the third one is 80 years later, when the biggest generation exits. So let's look again at our simulation. Well, let's actually look at the simulation and get our answer.
It seems like B is winning.
Okay, excellent. So people are already getting intuition. Okay, so as we run this forward now, we see that it happens a lot after. Here's the peak is minus 15. It happened here. The peak of population is happening at 25. So about 40 years after, minus 15 to 25 is 40 years. It's about 40 years after. So it's when this hump actually gets to be the mean age of the population. So there's good intuition there that I'm happy people got. So the lag there is about 40 years. Okay, learning to go back and forth here. Okay, and here's a mathematical explanation, which I'll skip since people got the intuition. And let's now look at what really happens for real population. So for Japan, which is one of the few populations that has had low fertility for a very long time, and where the low fertility is kicking into current population decline without a big migration effect. So the Cole scenario tells us that it should take about 25 years after fertility falls below replacement. So the birth peak is 15 years before, and it takes another 40 years, which gives us 25 years after replacement. But in Japan, fertility fell below replacement in the early 1970s, and the population didn't peak until, I think, 2009, 2010. So it took about 40 years. So what's wrong with Cole's scenario? Why is he saying it should be 25 years, and in reality, it's closer to 40 years? And the answer is that he wasn't intending to be realistic, but he left out two things that are a feature of actual populations going through depopulation. Okay, the first is longevity. So people are living longer at the same time that fertility is going down. And as people live longer, particularly at older ages, that doesn't affect the birth rate, the net reproduction rate. It's going to increase population size, and this will tilt the population curve upward a little bit, making the delay a little bit longer. And Tom and I do some mathematics and find an approximation that tells us this should be about 5 to 10 years. Then the second thing that goes on is that real world fertility decline differs from Cole's model. Fertility in China doesn't keep going down forever, according to the UN projections, nor in India does it go down forever, nor in Brazil does it go down forever. The UN thinks it's going to flatten out. And so one can have a different model of fertility decline, one that includes flattening, and that flattening, it turns out, increases the time it takes for population to peak by about another 5 to 10 years. Okay, so where are we now? Well, actually, I have time to go to the app and show you this, but let's look at the result first, and then we'll go back to the app. We have our birth peak that's happening at about 15 years ago. That's the first thing that we looked at. It takes about 40 years for that big cohort to grow up, so that gets us at plus 25 years. And then we have another 5 or 10 years from longevity and another 5 or 10 years from curvature, which these two things together about cancel out the minus 15, so we get back to about the 40 years, which is just what we saw in Japan. So
Josh,
yes.
Sorry for being impolite, but you asked me for the 15 sort of little bit minus warning.
Super, we're doing great with time. Thank you so much. Yeah, and so we're going to do one more look at what happens here when we introduce these longevity and curvature. So now we have our same projection. This is our projection with the regular exponential decline in NRR and no change in life expectancy. We have our peak at minus 15 for the births and our 40-year lag after births. Sorry, 25-year lag after the NRR is at 0. And we get a number like 25 here. Okay, so if we increase now longevity, it's going to tilt this blue curve up a little bit. And it tilted up a little bit. And it moves over a little bit. It changes from about 25 to about 30. Okay, and if we tilt it up even more by increasing life expectancy, then it becomes even later, from 25 to almost 30 to up more like 33. Okay, so that's what's going on when we increase longevity, and that's how we get another 5 or 10 years from longevity, which is what happened in Japan. The second thing we can do is we can ask, what will happen if there's more curvature here? So we can now the green line is more curvature and the gray line is the original curvature. And you see how fertility is flattening here. Now this is just an approximation to what really happens. It's much simpler than the UN model, but it gives us the effect we want. You see that as this flattens out, the peak moves over. So let's do that again. Here we're at 29, and as we flatten it out, we've moved up to 36. So we've moved out 5, 6, 7, 8 years. Okay, and if we have no mortality increase, it's a little bit cleaner. If we have too much, then fertility starts going up, and we have the program doesn't work. But as long as we have not too much curvature, then we get some increase from 25 up to 28 or 29. So another 3, 4, 5, 6, 7, 8, 9, 10 years is what we get from the curvature. Okay, now of course for a real population, we can calibrate these things and estimate how much curvature there is and how much life expectancy change there is, and use our formula to get a specific prediction for a specific country. Now, in fact, if we use the formula that we've developed, which I'm not showing you here, we can actually look at the predictions, and that's what this last. And in this case, the prediction lands right on, pretty much right on. It's the orange line, which you can't even see. If we can make it a little bit worse, maybe we can see the orange line. Not quite. Let's make our predictions a little bit worse by including mortality change. There we go. You can see it's a tiny bit different here, but the predictions are working pretty well, getting within a year or two, until you get very dramatic amounts of, say, longevity improvement or something like that. Okay, so we're done with our app. Your speaker is going at least happy about that because it's hard to switch back and forth. Let's see. And now we're going to stay on the slides for the rest of the talk. Okay, so how do we actually do in a real population? When I say real, it should be in quotation marks because these are actually forecasts of real populations. Okay, so here I have our biggest countries in the world, China and India, and also Brazil because it's a very smooth example of what's forecast to happen, and then the world here. And we see the pattern that we saw with the NRR of going down roughly exponentially with some flattening down here. The world is actually super linear, at least forecast by the UN. And we see peak births. In China, it was about 22 years before fertility was at replacement. In India, about 23 years before fertility was at replacement. In Brazil, about 21 years. So it's not quite the 15 that we predicted. There's some complications here because fertility was going up before it started going down. For the world where there's no kind of, the going up was so long before the replacement, it doesn't matter. And so we get it exactly right at about 15 years. And then if we look at the population, we see the lag here observed lag is going to be 42 for China, 39 for India, 41 for Brazil. And for the US, it actually is after 2100, so you don't actually see it, but it's about 40 years. And here are the forecasts from the formula I didn't show you, but if you do the analysis, you get these very close numbers to what is predicted. Okay, so I'm going to skip migration and we'll just conclude here. The first thing that we want to conclude is that it takes about 40 years for population size to start shrinking after a population has reached replacement fertility. And the Cole scenario says it should take about 25 years, but once we take into account the typical flattening of decline and typical increase in mortality, that comes out to be closer to 40 years. And that's what we saw in Japan, and that's what we're expected to see in China, India, Brazil, and the world. The second lesson here is we didn't really use any stable population theory. In fact, stable population theory, which gives us the theory of population momentum and many other things, is not really useful for this problem because we have constant change. This is a story about changing demography, not a story about demographic rates that stay the same. The third lesson, and I began working on this problem long before I found that Ansley Cole had already started on solved it in some sense, is that we need to reread the classics, and Cole 1972, 49 years ago, is one of them, and that oftentimes, because they were written at a different time, we have something now 50 years later to add to them. The same thing when we read Lotka or Keyfitz or Preston, or Ron Lee, or Jane Mencken, or Mendel Scheps, or any or I should mention great French demographers and great Spanish, great German demographers, great Spanish demographers. There are many that are worth rereading. And so let's just talk about some areas where there's work that can be done. So I've just talked about the peak timing of the timing of peak population. One can also look at other functions of the age structure, not the total number of people, but say something like the dependency ratio. So one could look at when does the demographic dividend, when is the highest, how long does it last? You could integrate the function under the curve and get a sense of how that changes. There's some more formal demography to do about what is the effect of the kind of ups and downs before fertility starts falling. What's the effect of the starting age structure? And so Shripad Tuljapurkar and others have done work that probably is very helpful to answer that. Aggregation. So when we look at the world population, it's made up of many subpopulations. Some of them are peaking early, some of them are peaking late. Do these things just average out, or is there something more complicated? How do we add them all up? And I think the last thing that we should think about is the current population forecasts are very complicated. They depend on, currently people are using hierarchical Bayesian models to forecast age-specific fertility, age-specific mortality. If we're interested in a very general question like when does population start declining, actually the kind of simple calculations that Tom and I are doing give you a very good answer. Given that we don't know what the rates are going to be, maybe we should just focus on the thing that really matters. So the thing that really matters here is when is T0? When is world population going to reach an NRR of 1? And if you tell me that, I can tell you when it's going to peak. The answer will be 40 years later. So a kind of simple stochastic forecast would be one in which we had a distribution about when the NRR reaches 1, and that's all that's the only parameter. And then we can say when the peak will be. It'll just be 40 years after that. Okay, thank you for listening to me. I apologize for maybe jumping around a little bit, but my last pitch would just be that the kind of things that we saw, for example, David Bloom talked about yesterday, where he's describing what's happening in all the countries at once. If we take a step back and think about the formal demography behind them, we'll see that actually they're the result of fairly universal processes. One of the amazing things about population decline or peak population is that it happens in about the same way everywhere around the world. No matter what the rate of decline is, remember it didn't change, the timing didn't change with K, it's going to be, these are kind of universals that depend on basic elements of actually the stationary population, what the mean age of the population is, what the time is when the NR equals 1, and what the mean generation length is of the stationary population. So these are kind of universal constants that help us gain insight onto a very general problem of why we have to wait so long for the population to start declining. Thank you.